Good morning.
Good morning.
How are you doing today, Jordan?
Pretty good. How about you?
I'm okay. Just hanging in there.
You staying busy?
I try to. Sometimes I'm just busy watching movies, that's it.
Well, that's a good kind of busy.
If somebody is having breakfast.
Is it audible? I'm sure it is.
Yeah.
Good morning, guys.
Good
Morning.
How is everybody?
I'm okay. How are you?
Doing all right this morning. Just did some yoga.
Okay.
Hello, can you guys hear me?
Yes.
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 Could you guys hear me before? I think my mic was off.
No.
I guess.
No, we
Oh, I
couldn't.
guess not. No.
I see. Okay. So I was talking for quite some time, and I was thinking it is my volume.
Oh.
I see. Okay. So okay, got it. So I realized it only when I asked how is midterm 2 going, and none of you answered, and it kept asking 3 times. So until then, whenever I was asking, someone else was talking at the same time, I suppose. Okay.
Well, I
How is
finished.
midterm 2 going?
Oh. I finished the 3 problems. I just need to read the paper and then finish that problem.
Okay. So it worked out well, I suppose, huh?
Yeah. Well, I don't know how I did on the 3 problems. I've done them, but
Yeah. But it's, I mean, if you feel a little confident, then that's reasonable, right?
yeah, I feel okay.
Because it's pretty much going through the steps, right? If I remember right, I don't remember the problems.
Mm-hmm.
Moses?
The gears one was a little tricky, but just
Little
thinking
tricky,
about,
huh?
yeah,
Yeah.
if you have a potential energy.
Yeah, that could be tricky. Yes, I can see that. Yeah. Agreed. Moses, how is it going?
It's going all right. I still need to do the third problem.
You still need to do what?
The third problem.
Third problem. The
Yeah. That was
third is the Kepler problem, right?
Yeah.
Yeah. Got it. Okay. Good. Okay. So, and there was a suggestion made by Moses that you guys want. It'll be nice if we can have some office hours for this class alone. Do others feel the same? Because Moses anyway meets me whenever he wants to. So the question is, do you guys want such a specific time?
I think anytime, any extra time to meet is not a bad thing.
Okay. How about 3 o'clock on Tuesdays? Today, 3 o'clock?
That'd be fine. That works for me.
It's a little harder for me, but if I need the help, I can try to arrange the time. Yeah, that's okay.
I think it is you and Moses who is most verbal about this. So maybe we can be flexible. So what's a suitable time for you, Jordan?
Like 5 a.m.
I might say yes to it. Don't-
Do people
don't be
even wake at
surprised.
that up early these days?
Yes. People
Yeah,
are.
I am up at that time.
We could do a 5 a.m. club. That'd be fine.
Wait, you too, Moses? Impressive.
I'm usually not up at 5 a.m. No,
Hmm.
but I'll be willing for you know, for the sake of
Well, I think 3 o'clock could work. I just would have to just if I had a question, know ahead of time. I don't want to put people out, you know. I think 3 p.m. would work. Plus I have class at 4, so it's not that unreasonable.
Oh, yeah, actually, we all have classes.
Okay. Okay,
So
and
you're
it is
talking
not
about our question session, isn't it? Like, off exam?
yes. If there is any questions for this course, you can meet at 3. You don't have to. It's not compulsory. If at least one of you guys is there, then I will be there. I might forget it because it's not routine for me. So just, I think Moses knows how to contact me. He just calls me. Because half the times it has happened that he was logged in, I'm logged in, but I'm not hearing anything because the audio doesn't work sort of. Yeah, so it should be possible to make it work. Okay.
okay. I might have a question. So I was talking with Jordan yesterday about the potpourri seminar that I'm going to be talking about. And I was just wondering if people could come to that. Like,
of course. No, I mean you can ask anyone for that.
well, I know it's an open thing. I just like particularly because we're covering kind of like an exam problem. That was my only consideration.
Oh yeah, it's okay. I mean it's open internet anyway, right? So
yeah,
it's okay. Yeah.
okay,
Yeah.
cool.
If the purpose is just to get the answer to the exam, even then it is okay. That is like discussion, but I was more thinking, oh, okay, you want to come, but yeah, either way is okay.
Okay.
Even if it is for the purpose of getting the answer for the exam, that's perfectly fine. Most probably you will give more than that, right?
Mm-hmm.
Yeah. Your title and the link was good, so it seems like you have done some. Yeah,
a little
feel
bit.
free.
I was
No
wondering
problem.
if maybe we could find a time to just kind of
Meet before.
go over it for me to practice.
Sure. Let's say, will you be there at 3 o'clock today? Then at that time we can talk about.
Yeah, 3 o'clock works for me.
Okay. Anyway, the discussion is about if others are not aware of it. Do others know about it? Moses?
I don't. What's happening?
Okay. So I suggested Moses that whatever so the midterm exam question 4, the negative masses, it's kind of a, what's the word for? All right.
Open
Weird solution.
Okay.
The solutions are weird there. I mean, it's not traditional stuff. So I suggested to him that will he feel comfortable talking giving a talk on it in a potpourri seminar. This is a math department seminar for those who don't know. I think Angela knows. Jordan and Avinash probably doesn't know. That they hold it almost every week in the math department. You can speak about anything practically, anything math related in principle, anything logic related. That's the best way to put it. And I thought this topic would be a good, thought-provoking talk for the audience. And so I suggested, and Moses was ready to pick it up. So we'll see how it goes. Yeah. It's just to, I don't think the idea is to say that there is negative mass possible. It's just that if it is, what are the implications?
Mm-hmm.
So, so we'll see. Yeah. And you guys also, if you guys think you have something interesting, you can always talk in that particular talk, as far as I know. Yeah.
So you're talking this Thursday, is it?
Yes, this Thursday, yeah. So he decided on the
Technically,
title.
till when is this semester going on? Till when is this going to end?
May 4th is a Monday, right? So May 9th is the last exam. And May 10th is graduation. So the semester ends on May 10th. Officially ends on May 10th. But the classes will end on May 1st, I think.
Mm-hmm.
Last day of classes is May 1st. Is that your question?
Yeah.
But most of us cannot travel, I suppose, right? So you're all stuck.
Everybody all of my friends who planned a trip to India, all of them got cancelled and they're all very sad.
Yeah. And it's tricky. Even if you end up going, you'll be quarantined there for a month or so, I guess.
Yeah, that's also there.
It's not.
I mean, it's okay if you just want to go home and relax and eat your mom's food, but if you had plans to visit your friends and later that it won't work.
True.
I don't want to keep talking, and then every time you take too much time in the beginning and then end up regretting it. So I stop talking.
Yeah, I was thinking I will start early, but I think these are relevant points, I guess.
Yeah.
Okay, so we want to change the topic completely. It's not a continuous stream of flow of thoughts. It's Kepler problem, and then suddenly we switch, and we want to talk about special relativity today. But before that, do I have any? I think all the due dates are flexible at this point, right? That's the only thing. No logistics, right? Okay, so let's. So we want to start what is typically called special relativity. And most of you have seen this in one form or the other in an undergraduate course. Otherwise, it is a very popular topic. So that leads me to ask, what is special relativity? What do you guys think is special relativity?
Same answer again, 1905.
Same what?
Same answer again, 1905.
Same. 1905 is when it came about, I suppose.
I said the same answer in E&M. So I said same answer again, 1905.
Oh yeah, that's some warning I have to, or what's that, disclaimer, right? I think I have taught this and in some form or the other in E&M undergraduate and E&M graduate. I usually don't teach it in E&M graduate, but this semester I did teach it in E&M graduate also. So for a couple of you, for Angela and Avinash, there will be a good amount of repetition here. but hopefully it is not that bad. Sometimes you gain, I guess. It's like, yeah, it's up to you guys. Yeah. Okay, so I cannot help that. Yeah. No, something more, let's say. What is special?
The behavior of massive objects near the speed of light, traveling near the speed of light.
Yeah, that's correct. How about this? Let's begin with this. What does special mean there, and what does relativity mean there? Why the topic is called special relativity? Or is it a misnomer, or is it a bad nomenclature, or does it have anything to do with what you have studied already on this topic?
Because it's a special case dealing with space-time, the curvature, right?
Yeah.
Am I wrong?
A little more. Yeah. Let's begin with relativity. How about that? What does relativity mean?
Space study of motion involving space and time. I'm not placing that properly, but space and time is there, right?
Yeah.
Are you going to say something, Jordan?
Go ahead. You can answer.
What I was going to say is, in relativity, we have two objects, two moving objects, and we look at the velocity of one with respect to the other, right? That's the relativity, right? And spatial relativity, we take a relativity condition when two or maybe it's just one, when one of the two objects is traveling at the speed of light.
And what happens?
Funny things happen, weird things happen, and that's what we're gonna talk.
What is so special about, yeah, Angela?
So the frame of reference, inertial frame remains the same, right? Or something like
the laws of physics are the same in all inertial reference frames.
Yeah, that's I think that's a very good, I think that's a summary of the whole thing. That's a perfect statement that laws of physics, whether it is described by Angela or Avinash or Jordan or Moses, they could be all in different places, and for that matter in different galaxies in different times. And if they are seeing the same thing, they should all describe it the same way. They might have it in different forms. The equation might look completely different, but it has to be the same. The conclusion has to be the same. And what are the conclusions that can be same? That's what relativity is about. Okay. Is there any other relativity you have seen before special relativity, historically speaking?
General relativity, GR, right?
No, that's later. That after. Historically, that's
Yeah.
after, right? General relativity is after.
Relativity of simultaneity or whatever.
No, that is part of special relativity. Yeah,
we'll
talk about that.
Is it Galilean relativity?
Yes, and what is Galilean relativity?
It's just normal relativity when the speed is very small.
Much less than the speed of light.
And much less than the speed of light.
What is different between the two? Yeah, I mean,
in Galilean relativity, the speed of the object can be as big as the object wants, but in special relativity, the highest speed is the speed of light.
Oh, so in Galilean relativity,
they're the same in all reference frames, right? The laws of motion are the same, no matter the reference frame. In Galilean,
Yeah, that statement remains the same in both relativity, special and Galilean. That laws of physics should remain the same in all inertial frames. That statement remains the same in Galilean relativity and in special relativity. And we'll make it more specific. But Anshula, you were asking something?
So from what Avinash said, it looked to me like in Galilean relativity, the speed could go beyond the speed of light. He said that it can be as much as the object point. Is that true? Is that how I understood it?
That's correct. That is true. That turns out to be the true statement.
Okay.
Yes. But what is more drastic about special relativity relative to Galilean? Speed of light doesn't even show up in Galilean relativity. Right?
I
So
think-
there is
Isn't
no
it Galilean
limit.
relativity just a constant speed, just a constant velocity?
Even special relativity, we will talk about. So we'll define Lorentz, inertial frame to be anything moving with constant velocity. So even special relativity discusses constant velocity frames or inertial frames. But what is very drastic, or whatever, Avinash uses the word funny, right? Funny things happen in special relativity. So what is, if you were to point it out, what really changed? What was the big deal? Suppose you had to point it to
Time?
some equation.
Time doesn't change?
Yeah, good, very good, exactly. And what happens what's the difference in time?
Time dilates
Yeah.
and length contracts.
Yeah, but better, make it better. Or
So
how
for
does
if
time
so-
work
Time
in
changes?
Time
So,
actually passes more slowly near the speed of light.
and at speed of light, there's no time. It's just infinite, right?
But
How
time is
about this?
absolute in Galilean, right? So it's not.
Yeah, I think that's the sentence I was looking for. All of you guys are saying the same thing, but one way of putting it
Time is not
that
relative.
Galilean time
Oh.
is the same for every observer in Galilean.
Hmm.
Okay, so let's begin with Galilean, right? So let's begin with the old Galilean relativity. Okay, how do you spell it? I think this is correct. Check that. Okay,
Yes.
am I right?
Yes.
Okay,
I'm the worst
thanks.
speller in the
Okay.
world, so I couldn't tell you.
That's better too. Okay, Galilean relativity. So let's, how about this? Let's derive Galilean relativity. Okay, we are not going to assume, by the way, what is Galilean relativity? Says that if you have two frames, so what we are talking about is there are two, first of all, maybe Lorentz, no, what is this? Inertial frame. Okay, so later we will call what is called local inertial frame. So this will be a common a terminology we will use. This is a frame moving moving with uniform velocity. Now, the moment I say this, uniform velocity, it has to be with respect to something, correct? If it's like I'm saying,
Yes.
it's a tautology, right? I have to define a frame with respect to other frames. So the point is that we have a lots of frame. So a frame moving with uniform velocity with respect to every other frame. So we are talking about a set of frames. So imagine infinite sets of frames. They are all moving with uniform velocity with each other. Is that clear? And we won't talk about accelerating frames at all. Okay, we will talk about acceleration, but all the frames we will have is of inertial frame in that sense, in the sense I've said that with respect to any other frame, it has a uniform velocity. Later in general relativity, these things change. Then we associate with what is called a local inertial frame, because sometimes that could be accelerating, and then you have to, at an instant, you can choose a frame which is at rest. But in special relativity, we'll talk about what is inertial frame. So we went from 3 topics. We're talking about special relativity, digress to Galilean relativity, and from there we digress to inertial frame. And next we talk about, there are 2 inertial frames. So let's say this is one frame, this could be Z, and this could be, let's say, X and Y is coming out of the board, right? And there could be another frame, which is X prime, Z prime, whose coordinates are given by X prime, Z prime, Y prime, and there is T also, remember, and there is T prime in here. When Galileo was working on this, or when Newton and Galileo were discussing these things, they never even imagined the situation that T and T prime could be different. That is to say that the watch in your hand and the watch in my hand could just read differently simply because we are traveling with respect to each other. They never envisioned that. So that was not even considered. Okay, so these days we say that's T is equal to T prime, and that's called absolute time. So what is Galilean relativity is, you say X is equal to X prime. So this is the solution if you want, but we want to justify this. Why is this? Okay. And let me put the other way, right? Let me put the primes this side.
It
X
isn't,
prime, Y prime. Huh?
isn't X prime equal to X minus the velocity times time, not X?
I'm going to put it Z prime equal to Z minus VT, if that is okay.
Oh, I see, because you're I gotcha. Okay.
So, yeah,
I
and I have to put the velocity also. One of them is moving, right? One of them is moving with velocity V, and they are seeing something, some event. So one frame is moving with respect to V is not the velocity of something that is happening. V is the velocity of the frame itself, and both of them observe some event, right? So this could be an event, like someone is walking, that's an event, right? Someone is walking, and an event has to happen in a time. So let us say usually between 2 events is what a physical process happens. Correct. Someone begins to walk and stops to walk. So that could be that process. The cross with a circle is an event, could be anything. And they both observe. Whatever they both observe, for example, F is equal to ma is an equation. They describe that process with that equation. The difference between the 2 observers should be explainable using these transformations. And T prime is equal to T. That's Galilean relativity. Okay, so if, for example, the observation could be that, yeah, one of the classic observations that Galileo himself made is that velocity is relative. Correct. If I am, if a car is approaching me, I would say that car is approaching me. But if you're sitting in the other car, they would think that I'm approaching them, right? And there is no way of differentiating this. If you are in space, there is no reference points. There is no way of differentiating who is moving. Okay, and that Galileo himself made it very clear, and he gave the, in those days you didn't have cars. At that time it was ships were prevalent, and he said that if you were in the underground of the ship and there was no motion, if you were if it was sailing very steadily, and if you were to throw a ball up in the air, the question asked is, will it come back in your hand or not? Is that clear what I'm asking?
Mm-hmm.
If a ship is sailing, or let's forget the ship. You're sitting in the car, right? You're sitting in the car. The car is moving on the interstate. You're on the passenger seat. You have a ball in your hand. You throw it vertically up, exactly vertically up for you, right? That is a vertical with respect to you. You throw it up. Will the ball come back in your hands?
Yes.
Right? It comes back, and it will come back in your hand. And if there was an observer outside the car seeing the whole thing, he will see that this ball would actually take a parabolic trajectory. So this would go up and come here, but you're actually in the car. You threw it vertically up. So with respect to you, it would have gone vertically up and come down. But for an observer who is sitting outside, it takes a parabolic path. So that velocity relation, v of a with respect to ground, let's say v of a with respect to b is equal to velocity of a with respect to ground minus a velocity of b with respect to ground, right? So this should be read as a. So this is velocity of a with respect to b. That's a relation. That's like a physics. That's like coming out of an observation. This equation might look different for different people, but the conclusion has to be the same. That's what relativity is about. Like if you start from, you should be able to go from one observer's conclusion to the other observer's conclusion just by using these equation, and which is easy to see here. If you were to write, start from the third equation, z prime is equal to z minus vt, and here v in this case would be v of a times b, right? V of a with respect to b. Take a derivative, so you get dz prime over dt is equal to dz over dt minus vab, right? Vab. And since we want to compare this with this, let me define z with respect to t as velocity of a with respect to the ground. I didn't specify clearly in a diagram, but let's say this is velocity of a with respect to ground, and this could be velocity of b with respect to ground, and that's velocity of oh, this doesn't come out, so this is ab, right? This is ab. Right, so that's an example where you can explain what one observes with respect to the other using this coordinate transformation. Okay. But let's go back and suppose we have to justify, because we are going to change this, right? These equations are going to change under relativity. Primarily, what are the equations that change in this? The third and the fourth, especially the fourth. Time is not going to be absolute. Okay, so and we are going to justify that. So if we are going to go and change this equation as well, let's see how much can we justify these equations itself, or in a sense, can we derive these equations based on some basic principles. Okay, so let's begin with that. And once I derive those, at the final stage, we will introduce one more principle to it and change this whole equation. Okay, so that will be the idea. Any questions at this stage? Okay, clear. Okay, so let's so our goal is that between two inertial frames, we want to write a transformation. In general, you can have x prime could be a function of x, y, z, and t, right? like it is actually x prime is equal to x, but to begin with, it could be any function. Right? And same thing with y prime, could be any function, and z prime. So let me explicitly write this out, but we're going to simplify these things very quickly. And t prime, so this is the new feature which was not even attempted before. It was taken for granted that this will be the same, but we allow this to be a function of x, y, z, and t. Okay, that's the new thing. But we are now trying to derive Galilean. So the first requirement we make is that again every every inertial frame has to see the same thing, or has to see the same thing in the sense that it has to be relative. And what is the best thing we can do? We would like to say that whatever I see in here has to be the same as what I see in another galaxy. So a translation in position or time should not matter, right? If I have an inertial frame, I move it a little to the right, a little bit more to the right, and still I should see the same physics going on. If something is not accelerating in one frame, it should not accelerate in the other frame either, right? That's a requirement, and it and we require the idea that the space and time is homogeneous. Right? Even though space, strictly speaking, is not, that is more matter around us. But as far as the inertial frames go, we will say that the kind of inertial frames we can imagine, they're all uniform, that is homogeneity in this whole thing. And this changes to a certain extent when that's the difference between general relativity and special relativity. It significantly changes. But for now, we say that it is homogeneous both in space and time. And that makes the requirement that this cannot be as general as we wrote here. They have to be linear. Okay, so this requires us to say that x prime has to be some constant a. So let's say a11 times x plus a12 times y plus a13 times z plus a14 times t, and that could be a constant also, right? So let's say that as a15. That's a lot of constants. Same thing for y prime. I can have the same set. Let's call it a21 x and so on. I think I don't have to write that explicitly. It's clear enough. And this is a31 x plus so on. And t prime, the important one, which will play a big role in special relativity, is a41 x plus so on. Right? That's what you gain from this. Now, next, notice. So what we are now saying is that if you have this diagram like we just still in the frame, that is equivalent to saying that you have this two reference frame, and I can tilt it as much as I want. Correct. So the one could be tilted in this sense, and it is still going in this direction. But I have isotropy in space, which can tell me that I can actually rotate these frames. So there is a choice in these frames that allows me to choose my x, y however I want. At least once I have that choice, right? So if I were to, since something is moving linearly in one dimension, especially when we are talking with the other frame, I have this choice that I can set x and x prime in a certain way. A whole motion is happening in z and z prime, and time also comes into picture. I can choose x and y perpendicular to that, and you don't lose any information there. You don't lose any generality. And requiring that, immediately you can say that, oh, there is no y and z and t dependence in x prime. Okay, so that is so this is, if you want, you can say this is a choice, or you can say this is an isotropy you're invoking. So if you were to invoke isotropy, then you're basically concluding that there is x prime is equal to, I still can have it scaled, but then let's also require that at time t equal to 0, it starts from the same place as the other frame started. So let's say plus at t equal to 0, they were all overlapping. So there are those restrictions, so frames are overlapping. At t equal to 0, the frames are overlapping. Okay, and if you use those conditions, you can show that x prime is equal to x, y prime is equal to y. Okay, and z prime can be anything now, and it will be basically A3 or A32, right? A31, A32, or A33 basically. But let me change my labels now. This is A times Z plus B times T. That is all there is to it. Eventually, what we are concluding is that based on very reasonable choices, you can show that all the transformation has to be in Z prime and T prime. And the main idea is that we are allowing this time to be different. Yeah, even though we're working with a Galilean relativity, A, B, C, D, let's say E times Z plus F times T. Okay, that's good enough. Let's next say the following, and we are going to say the following. Yeah, so let's say this. So the third requirement is that, again, remember we are doing Galilean, like it's the first thing you'd study in introductory physics, I suppose. So, okay. So next we show, and again, this I'm lucky that this diagram is still in the frame. Let's think of a particle here which is going with the same velocity as the velocity of the frame itself. So maybe let me talk about this. So we have a frame here. So there is Z and X. There is another frame which is moving with velocity V, and that's X prime and Z prime. And we are observing a particle moving with velocity V. It's very clear what we would say. We would say that as far as the X frame goes, he or she would say this is X, or sorry, Z is equal to VT. Right? That will be the description of the particle that's down here. And we also know for sure that this is at rest with respect to the primed frame. If it is at rest, if we choose that to be at the origin itself, this is going to be either a constant or we can choose it to be 0. This is an identity. Like if you are in the rest frame, it is not moving. Either Z prime is a constant, or if you choose it to be at the origin, it is 0. Right? That's a requirement. That's like an initial condition. Whatever transformation you come up with, it better explain this. It explains the fact that something is going uniformly. We will see it as Z equal to VT, and another frame will see it, and the frame which is moving with the same velocity as the particle itself will see it at rest. Okay, so that's a requirement we make, that whatever
At this point,
physics
the third point.
Okay, so we have two frames. Again, we are doing Galilean, and this will hold in special relativity also. I'm deriving this in the context of Galilean, but all this goes through in special relativity. Okay, I'm saying I'm interested in a transformation which will explain relativity, but whatever it is, if
Lorentz
there is a
transformation.
particle, huh?
Lorentz transformation.
Yes, Lorentz transformation, but I'm deriving this, I'm claiming that I'm going to do Galilean relativity and at the end change something and get Lorentz, okay? So
Okay.
all the conditions I'm using as of now are applicable to Galilean and relativity. I'll make it very clear when I switch from that. So the question is, so what is the requirement we are making for both Galilean and special relativity is that if there is a particle moving with the same velocity as the second frame, it should seem like it is at rest to the second frame. That's a requirement we make for this transformations. It better explain that because we believe that that has to be true. Otherwise, it doesn't make sense. Kind of. Okay, so that's a requirement we make. Is that clear? So this is a particle that's moving. So in the first frame, it should see it as z equal to vt. And in the second frame, since it is at rest, it should show up as z prime equal to a constant, or we can choose it to be at the origin, and that's a requirement. So if that is the case, let's put that in, right? That's a requirement now. So put that in the first equations and we learn something, correct? So if we substitute that, z prime is equal to 0, right? And a times z, that is a times vt, plus b times t is 0. So we learned something. So time t is not 0. So b has to be equal to a times v. Right. So b has to be equal to minus a times v. Okay. I can not do the same thing in this equation. So what we have as of now is that z prime is equal to a times z minus a times vt, which means to say that a times z minus vt, correct? So we almost have it except for this factor of a, right? We cannot specify that, but it seems if a was 1, then that's Galilean relativity, except at least for the position piece. We have not yet set t equal to t prime. Agreed? Now, so that's 3 conditions we have invoked. Let's invoke some more, right? What else can we think of in this? So let's go to the new code space. Any comments as of now? Questions?
Oh.
Okay. Yes. Is there?
I just said no. I think
Yeah.
I'm okay.
Okay. So now let's require that. So this is so there are 2 frames here, right? So this is z, and let me just call it. And there's another frame z prime that's moving with velocity v. Now what we require is that if I were to, with respect to this, the primed frame is moving with velocity v, it is necessary that we require this, even though in the first part I said the velocity relation is a conclusion from Galilean relativity. Here I invoke that with respect to z prime, if I'm sitting in the primed frame, I should see this to be moving the opposite way with respect to z. These 2 should be the same. As far as the equations go, this property should come up. So how do you see this property? So here is at least in the z and z prime. If I were to switch or swap, right, all the z's with z primes and all the z primes with z, I'm not just replacing z with z primes with z. So I'm swapping the frames, right? I also do t and t prime. I swap them. That's equivalent to changing the sign of v to negative v. Okay, that's again a requirement I make. I say that whatever transformations I'm looking for, this should have this property. That is equivalent to saying the inverse of this transformation should be equal to what can be obtained by just by putting v equal to minus v. Okay, so we are looking for a transformation. It has an inverse. Mathematically speaking, it has an inverse. This is a matrix relation, if you want. That inverse is simply got by minus v. Is that clear? What is the rationale for requiring that? Again, that's in this way of deriving, that's a requirement I'm making. We already found a relation for z prime. So let's say z prime was equal to a times z minus vt. There was a relation for time also, but we couldn't simplify that too much. That was a still there is a e times that stays as it is. We haven't learned anything about that. But in this equation, if I were to flip this, what happens is, so use this property. So z prime becomes z, a remains the same, right? Or whatever a is, it changes sign there. That is the only thing that happens. And this is z prime. V changes sign, so it's plus v times t prime. Is that clear? Okay, that's under the requirement that all these frames inverse of the transformation should be explained using this. Okay, good. Okay, so now this is what we have as of now. And what can we do now? This is where now the derivation we are doing until this stage is true for both Galilean and special, as I repeatedly said. Now this is where we change or switch or bifurcate, right? Now we require that, let's say, so suppose we were doing Galilean. So Galileo comes and says, he didn't specify say it because it was just taken for granted at that time. At that time, they didn't even deal with this time. Time was put outside this whole transformation. They dealt with only, or intuitively, they said t prime is equal to t. So Galileo said that t prime is equal to t. Correct? And immediately, so if t prime is equal to t, if Galileo says that, then if you want to satisfy these two equations, so t prime is now equal to t, add these two equations, so you get, so if you do that, so let's, so this has become t prime, right? Suppose, how do I do this? So yeah, so I'll add these two equations and I'll get z prime plus z is equal to a times z plus z prime, correct? Because vt cancels out if t was equal to t prime. And this immediately implies a is equal to 1, correct? And that's Galilean relativity, correct? And you get Galilean transformation, and you immediately get Galilean transformation. Oh, maybe I should go back and see what happens to the other terms, right? So this immediately tells me that a is equal to 1, but we still did not explore the other equation, right? We had a time equation also. So this implies that z prime is equal to z minus vt, and t prime all the way back, right? T prime was e times z plus f times t, right? Let's see. Yeah, just by requiring t prime equal to t, I've killed f, right? So just by requiring t prime equal to t, I necessarily require e is equal to 0 and f is equal to 1, right? So that's Galilean relativity. Okay, Anshula, you're making faces.
No, I'm just trying to figure it out. It's okay.
Yeah, is that clear? Okay, so basically, the moment you say t prime equal to t, you get your Galilean transformation.
Yeah, okay, I see. Yep.
Okay, but that's not what we want to do. We want to keep all the logic that went until here, and we want to come back. Like now, we are saying we're changing our requirement. One more requirement. That's just one more requirement, and that's it's amazing how just one small tiny requirement changes everything. Okay, and what's the requirement? Anyone? Any guesses?
That f is not equal to 1.
Yeah. Oh, of course, in this transformation, yeah, f won't be equal to 1. That's correct. But again, what is the motivation here? Remember, there was one of the things we used is this, correct? That something going with constant velocity should, or the specific velocity of that frame should look as if it is at rest. That's a requirement. But now there is a new requirement. And remember, historically, what was happening, Maxwell gave his equations in 1865, right? In which speed of light was a constant, right? Just to motivate that. So this is the fifth condition that we're going to put. Maxwell gave his equation. It came out to be a constant. Like the whole subject of special relativity fits in very perfectly only in electromagnetism, right? Because that was where it originated. C is equal to constant, but the big leap made by Einstein is that he had nothing, he detached the whole relativity out of electromagnetism. It's sort of ironical, or it's kind of counterintuitive. It came out of electromagnetism, but the contribution of Einstein is that he said this has nothing to do with electromagnetism, even though it had everything to do with that in a sense. So C is equal to a constant, okay? That's a speed. And we are talking about inertial frames which are moving. We said there is an infinite set of inertial frames. We can move as any velocity that you want to. But now Maxwell says that there is a special speed. In what sense is it special? It looks the same to everyone. If you were looking at light, all of us see the same thing. If you measure the speed of light, it comes out to be the same. And that has to be incorporated in this equation. Correct? So this is the requirement. So based on Maxwell's conclusion, and that went on for 35 years, 40 years, right? In 1865, he gave it, and until 1905, they struggled with this. And this is what we want to explain, that if you are in the first frame, there is a light particle moving with speed of light. There's a wave, optical wave that is moving with speed of light. You will say that, oh, that Z is equal to CT. That's what the first frame will say, right? What will the second frame say? That Z prime is equal to CT. No relativity in them, right? Both see exactly the same equation. And we put that as a requirement there. Otherwise, all the arguments we went goes through, but now we have a new requirement. Okay? New requirement that light looks exactly the same to both or the equation governing the light is exactly the same. Is that clear?
Mm-hmm.
So now let's see what happens if we were to impose this equation, this condition in our, am I still in the board space? Yes, I am.
Maybe I'm not connected the joints properly, but I thought Z prime is 0. Why is it ZT prime now? I mean, I see that light has to remain the same in every frame,
yeah.
but Z prime is the position of the object, right?
Even then, that's the point. Why would it be Z? I mean, okay, here it was moving with velocity V, so we said it is 0.
Oh, okay.
Right?
Okay.
A particle that is moving with velocity V to someone who is also moving with velocity v will turn out to be at rest. Now we are seeing speed of light, and it turns out to be the maximum, but we have not made that requirement. The only requirement we are saying is that if there is something moving with speed of light, it will turn out to be moving with speed of light even to someone else, relative, who is moving with respect to us. That's a requirement, right? Basically, in the second postulate, if you notice, I mean, as a postulate, Einstein says that speed of light is a constant to every observer. That's the statement. This is the second postulate of relativity, if you want, of special relativity. Okay, that these two equations has to be satisfied. So that's the second postulate, if you want, and that's where we deviate from general or any other relativity, and the only other relativity we have here is Galilean relativity. And let's see what we can conclude from these equations. Any other questions? Okay, so let's substitute in here. Wherever I see z prime, I put a ct prime, and wherever I see a c, I'll put ct. Okay, that's what I'm going to do. So that's z prime is ct prime. That's equal to a. Right, let me write it to the left so that maybe I can use the space that remains. So c times equal to z is a c times t, so I can pull out a t afterwards. T, and right, that's the first equation, and the second equation here will give me c times t is equal to a times t prime now, or c plus v. Okay. Great. So that's an equation or two equations, and there is only one unknown. So there is a constraint there, right? So let's multiply these two equations. Like usually you add or subtract. Let's multiply these two equations. That way what happens is that there is a t and a t prime that comes on the left. T and a t prime comes on the right. That cancels out. And we have c square is equal to a square times c square minus v square. So there is a new solution. That's what Einstein realized, that just by changing one small thing, that speed of light has to be constant. That's a second postulate of relativity. Otherwise, most of the other parts of relativity can be credited to Galileo itself. But this small change changes the whole transformations, and a now is equal to, so a is equal to 1 over 1 minus v square over c square. Okay. We will often call this gamma. Okay, we will call it gamma. But for now, we will keep calling it a, but that's going to be gamma. Okay. So z prime is equal to gamma times z minus vt, or z prime is a times z minus vt, right? What about the time transformation based on this? Now we can go back and see what can we conclude about the time. Okay, but before that, is that very clear? These are the arguments that goes through. It's very important to appreciate the fact that relativity principle existed before Einstein, can be credited all the way to Galileo, and what Einstein did is that he based on the observation that C is equal to constant coming out of Maxwell's equation, he proposed that these two equations should remain the same. And that leads to Lorentz transformation. So basically the moment A is equal to this, that's practically Lorentz transformation. But I will add on, I'll finish it up by finding out the E and F in this case, right? So we still have to find the transformation property of the T, but that's just a matter of finishing things up. Okay, so let's go back, or let's go to the second. Oh, I erased my time equation. Bad. bad. Okay, I think it was this. So what we have as of now is Z prime is equal to A.
You'll have to move the board or move the camera.
I have to move the board, of course. I have to move the board, otherwise you guys cannot see it. Okay. Yeah, so Z prime is equal to A times Z minus VT, right? This is what we have derived. And A here is equal to 1 over 1 minus V square over C square. And we still have not figured out T prime. We said was some E times Z plus F times T. Or before I write that, we figured out one more equation. Let me write that down also, so that will be helpful, I suppose. We also have Z is equal to A times Z prime plus V times T prime. Correct. That was because the inverse has to be true. And so A we have figured out, so all these equations are correct. Now T prime, we left it in between. We did not pursue it too much, but let's go back and pursue that. Okay. So that's F times T. That was our equation. Let's substitute, right? So we can stay. This can stay, or how do I do this? Help. I'll do substitute this in there and Z prime. So yeah.
Or can we just substitute CT in for Z?
CT. Oh yeah, I can do that also, right? Yeah, that's correct. I can do that also. Z is equal to CT. Yeah, is that a short way, or what are you suggesting again? So I have to find E and F, correct?
Mm-hmm.
So if I put CT here, right? CT. So yeah, so let's do that. Yeah. So surely Z is CT, correct? So I can say T prime is equal to E, or at least that has to be true. So CT plus F times T, correct? What does that give us? So that tells us, yeah, that doesn't tell us much, right? That's just tells us that, so this is EC plus F times T, correct? Okay, that's fine. But let's do the following. I think that maybe there is a shorter way, but let's try to put Z prime into this and T prime into this, right? So that will be a constraint we will get, I suppose. So what I'm doing is Z prime in this equation and T prime in this equation. So everything will be in Z and T, and there will be a constraint that will come up. Okay. So Z is equal to A times Z prime. Z prime is nothing but A times Z minus VT plus A times V times T prime is EZ times FT. So that's a connection, that is z and t coming in. So all the coefficients of z and t has to be 0, right? So put everything onto the left, let's say. So that is z times 1 minus a square and minus av times e, right? So that's the coefficient of z, and plus coefficient of t is a square times v from here, and that is minus a v f times, that has to be equal to 0. Right? And this is true for all z's and t's. If this equation has to be satisfied, the coefficients of individual z and t should be 0. From this immediately, it is clear that this implies that f has to be equal to a. Right? Av is there in both, so f is surely equal to a, and e apparently is equal to 1 minus a square over a times v. Correct? And what is that? So that's equal to 1, so 1 over a times v times 1 minus 1 over 1 minus v square over c square. Right? So 1 minus v square over c square minus 1, so there's a minus v square c square that survives. Correct? So that's 1 over a times v. There's a v over c minus v over c in the numerator, and 1 minus v square over c square, which is a square, right? So am I still, yeah, I can still keep writing.
Should it not be minus v square over c square?
Oh yeah, v square over c square, that's correct. Minus v square over c square. I was foreseeing the cancellation. Okay, but equal to, this is a square, so this is basically one of the v cancels out, so that's minus v over c square times a. Correct? And since we used gamma, so our final transformations are z prime is equal to gamma times z minus vt, and t prime is equal to f is a, e is also having an a, so that is a gamma in both, so that's gamma coming out, and and what is t prime, so that's z, e is this, so that's minus v over c square times z, right, minus minus t. Okay. That's because of the dimensions, that slight clutter that's showing up there is for the dimensions, because it has to have the dimension of time. V over c is dimensionless, so you want to put it the other way. So we can change that a little bit. So we, the way we will write it is, let's put a speed of light, let's always have time coming with c, and let's introduce a new dimensionless quantity, is v over. Okay, whenever we look at beta, we should think of it as speed, okay, or velocity. So this is going to be gamma times z minus beta times ct, right? I multiplied by c divided by a c, so that gives me a beta there. And this equation pretty much c times t prime is equal to gamma times minus beta z. Oh, this should be plus, right? This should be plus here.
I think it should be plus, yeah.
Yeah, thank you. That should be plus. Yeah, that's plus. And that's Lorentz transformation. Okay, so again, if you go back to your whole argument, what we are saying is that using the principle of relativity is required that everything should look the same, and based on homogeneity, and basic idea is that something that is moving with the same speed as the other frame, then it should look at seem like it is at rest. And the idea that light looks the same to everyone leads to what we define as the Lorentz transformation. Okay, so let's me write that down. So the summary is that principle of relativity requires the transformations to be z prime is equal to gamma times c minus beta times ct, and t prime, instead of t prime we will say c times t prime. So just scale it so that always it's a distance. The dimension of c times t prime is distance. So it's gamma times minus beta z and plus c times t. This can be easily, and of course there is x prime is equal to x and y prime is equal to y. That stays. This can be nicely compiled into a matrix equation, and let me write it as let's for once write this total, right? So this is x prime, y prime, z prime, and ct prime. So this is only in the z direction. So the velocity in principle could be in any having a combination of all this direction also. But if it is in the direction, so that's 1, 0, 0, 0. Oh, not 0. This is 1, 0. Here you have gamma. This is minus beta gamma, minus beta gamma, gamma. Like linear transformation can always be represented using matrices. Correct.
I'm just a bit confused because I thought, well, doesn't CT prime equal Z prime?
CT prime. Yeah, CT prime is equal Z prime. That doesn't spoil this, correct?
No, it doesn't.
Change. Yeah. So,
but then in our matrix equation, we have two quantities that are the same.
Why do you say that? This is because this is the same equation as this. Like
yeah.
Z prime is 0 times this, 0 times this, gamma times Z minus beta times. Maybe I'm not getting the question. Ask me again. I sort of see what you're suggesting. Yes, you're worried
I guess
that
it's just it's just a
yeah,
small
you're worried
confusion.
that, oh, how does this work? This has to be still satisfied. This is still true.
Yeah.
Yeah, that's okay.
I guess what I was like, couldn't you replace CT prime with Z prime and have two Z primes in the matrix? Yeah. You could do that, and that would also
you will be fine, but you will be probably taking away some information there.
Okay.
But that's okay. You are allowed to do that.
Okay. Yeah.
Yeah.
All right.
Good
Yeah.
point.
Cool.
You're allowed to do that actually. Yeah. I mean, often we don't see it, but it has to be consistent because we use that condition,
Mm-hmm.
right, to derive that. So that's inbuilt in there, right? And one should also realize that this is for, see, when this is a particular case where the speed of light is going, but light is always there in every system we consider. We can always envision a light moving adjacent to it, and this equation is valid. Yes. Okay. But in this case, these are disjoint equations, so it doesn't hurt much. Yeah. Okay. Yeah. I think so. Yeah. Be critical about that. Okay. Like in what sense is it? Okay. So that's and 1057. Really? Yeah, that's Lorentz transformations. Okay. And really, it's already 1050. Yeah. Yeah. Let's stop here. I suppose that's a good place to stop. Next time we'll talk about the consequences of Lorentz transformation.
I forgot. Does this Lorentz have, or is it just in the name? Is this Lorentz spelled L-O-R-E-N?
Oh yeah, good point. Yes,
or is there
this is the Lorentz who was very influential.
Okay.
Lorentz, very reputed. I mean, the interesting part in history is that in 1875, so there is a few, so this is called Lorentz transformation.
Mm-hmm.
But so there is Heaviside who plays a role. Heaviside wrote down the transformation of electric fields. We are not talking about electric field here. So suppose there is a point charge moving. So this was Einstein's idea that, or which was already there in Heaviside's work, is that a positive charge which is at rest has an electric field, right? So it looks like this. Okay. So that's how an electric field of a point charge looks, the standard classic electric field. But now if the positive charge was moving, okay, what Heaviside derived, which is practically an immediate conclusion of Maxwell, but it took about 10 years to bring this into a very nice form, and that was primarily done by Heaviside. And he showed that in this context, whatever we are talking about, what it turns out is that the electric field gets squeezed in the direction of motion, right? The electric field is like this. Right, so it's basically an ellipsoid now. So this is a sphere, right? If you were to draw an electric field for a point charge, that is a description in terms of a sphere. That means to say that every point equidistant from the center of the charge will have the same strength of electric field. But that's not what happens when it is moving. It is it's an ellipsoid. The distances on an ellipsoid at every point on an ellipsoid around that point charge, that has the same magnitude of electric field. And Lorentz saw this. Lorentz even had this transformation with him. Poincaré had the velocity addition. Every reputed person, they all had all the equations right in front of them. But what is the contribution of Einstein is that he detached himself from the electromagnetism completely, and he saw it as a principle of relativity. He said that this has nothing to do with it. It's just an artifact of the fact that speed of light is constant. There is a signal which has a limited velocity, and we cannot help, but we are using that to see things. So our observations will change, and the principle of relativity deals with that. And that's the importance of special relativity. And that brought in a lot of predictions. And we will see that we can accept this, but then immediately this leads to a lot of what Avinash called funny things, right? A lot of very counterintuitive conclusions come out of this. And they were verified one after the other. Each one of the conclusions were verified. There are lots of them that stay unverified too. So there is a lot of debate on what is going on. But it is very like, it seems like this has to be true. This is how our nature works. It seems to be a big consensus that this is how it is. Many conclusions has been verified. And the most famous is the E is equal to mc square, where you can create an atomic bomb, and that comes out of this. Okay.
So Lorentz
what we
realized
know.
that Maxwell's equations were invariant under the transformation.
Yes. So now what happens is that, okay, so this is how historically it goes. So this is the bias everyone had. Maxwell wrote his equation down, and Maxwell himself wrote a wave equation. Okay. So he wrote a wave equation for electromagnetic waves. So 1865 comes Maxwell. In 1865 itself, theoretically, it is clear that there exist waves that travel at the speed of light. And immediately radio was invented. Radio was invented within 10 years by, what's this guy's name? Hertz, right? Hertz was the first person to show inside a room that without any wires connecting them, there could be a signal that could go from one to the other using LCR circuits, oscillations, and so on, right? So radio was invented immediately. So we know that there is electromagnetic wave. And now here is a bias. We know sound. We know sound very well. Sound goes through a medium. And you immediately say that, oh, there is a medium in which is all this electric permittivity and magnetic permeability is the property of a medium. And this medium is through which light is going. And we want to study that medium. And there were experiments built. This is the famous Michelson-Morley experiment. Was built to study that medium. That is called ether now. Like even in those days, it was called ether. So everyone, including Lorentz, Lorentz was extremely reputed. He had contributed a lot to electromagnetism. Everyone was looking for ether, and everyone was interpreting this in the context of ether. They were all biased. And there was all the reason for Maxwell's equations to be modified rather than Newton's equations to be modified. Newton was 200 years old equation. So it was not expected. No one expected that it's going to be Newton's equations that's going to be changing, not Maxwell's. That's sort of an irony that it was so well based, but it did not stand the time. So it took a very bold visualization, bold intuition, I would say, Einstein could see this clearly as not being part of ether. It has nothing to do with ether, nothing to do with ENM either, electromagnetism either. Instead, he said there is a signal that travels, that looks the same to everyone. So whatever Lorentz transformation is applicable to anything. It doesn't have to be electromagnetism. For example, gravitational waves, right? Gravitational waves come out of some other equations, entirely different equations. What's the guarantee that the wave that is there should travel at the same speed as Maxwell? No guarantee. But once we say that there is a maximum speed or there is a constant speed which looks the same, that has to be true for everything. And you conclude that gravitational waves also has to travel at the same speed of, with the speed of light. And which is true as of today. We know that it travels at the speed of light. So yeah, it's just that the time was different. If Maxwell had given his equation 100 years back during the times of Galileo or something, it would have been obvious, oh, this is relativity. But at that time, there was so much bias towards the ether or looking for a medium that no one saw through it.
So Maxwell's equations are not invariant under the Galilean transformations then?
They are not, but they are invariant under Lorentz transformation. Yeah, I didn't use the language invariant. Invariant means doesn't change. The form of the equation, or invariant has to do with it doesn't change at all. And covariant has to do with x gets replaced with x prime, t gets replaced with t prime. The form of the equations remain the same. That's called covariance. Invariance would mean that it doesn't change at all. So it's a number sort of. So the correct language would be Maxwell's equations are covariant under Lorentz transformation. But you meant it. You meant to say that. Yeah.
Okay.
I got to run, guys, but
Yes.
I will see you at 3.
3. Okay. Yes.
Cool.
Anyone is welcome to be there at 3.
Awesome.
Okay. Only if you want to. You don't have to.
So it must have
Or
been
you want to hang
really,
out. If you want to hang out,
Oh.
that's another thing. Yeah.
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 Okay.
Go ahead, Charlie.
so it must have been really confusing because I remember doing, I remember studying a little bit about Christian Huygens and how the light propagates similar to sound, and how, you know, when you look at the slit experiments, how you could explain the mechanics
Correct.
as like little wave packets. It's so surprising to me that they were able to figure it out relatively quick.
Yeah.
That wasn't, you know, even though it explained reflection and refraction of light, it was still wrong. It's like
yes. Okay. Maybe in this context, the way I have to say is that, okay, now what Huygens did is that he suggested that light is a wave. Okay. All the properties of light that we know can be explained by claiming that this is a wave exactly like a sound wave. But any wave has a velocity associated with it, right? Velocity of the wave. And what relativity is invoking is just that speed. Relativity doesn't say whether light is a wave or a particle. It doesn't say anything about it, if that helps you. So Huygens is not touched by this relativity principle as of now. Okay. Does that help?
Yeah,
So,
yeah, that helps.
So that whole interpretation is safe, is everything is consistent with relativity.
Wait, isn't he the guy who gave the idea of wave fronts?
Yeah,
That's correct.
So-
Huygens, yeah, I don't know how to
Basically,
pronounce his name.
a bunch of small Huygens sources propagate the which can create planar waves. If you look at each point, there's a Huygens source.
What are you saying? Hooligan source?
I think he meant, I think, I don't know how to pronounce it. I think probably Jordan is doing it the right way. I think he's meaning Huygens. So this is, I think I when I was in high school, I always said Huygens. So
How is pronounced? Huygen.
I think it's Huygens, but I don't know.
Huygens. That's how they pronounce it in Dutch.
I think so.
I've been told that G is silent, but I don't count on me. Okay.
Could be Huygens.
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 Yeah, Huygens. Yeah, but I am not good at this. I'm horrible in language. Especially these days, I see myself in video. Sometimes I have to hear myself, and I hate to hear myself. I never knew I was that bad.
No,
I
you sound
have-
fine.
Regarding the midterm question that I wrote to you about, email.
Oh, yes,
Can I
yes,
ask
yes.
that? Yeah. I approached the other way that you mentioned. Even then, I'm getting stuck. There is some additional cos theta sitting in front of the derivative. I don't know what to do about that. So
Yeah, you want to do that now?
I don't know. Maybe if.
Yeah, I can try that. I didn't try that though.
Oh.
it was easy for me to just give some suggestions and leave it there. So
Because
this is
contour integral is working out pretty good, except for that 2 factor that's coming. I don't know what to do about that.
that factor of 2 is why do you do that in the beginning? That's
So
wrong, right?
the integral is from 0 to 2 pi, right? So if I make a substitution cos theta equal to z equal to e power I theta, then the integral is running from 0 to 0, right?
You can
Not
use
necessarily. We have to be very careful, right? Where z is, if there is a square root of z somewhere, then it could be pi also. But it is from 0 to 0, but then it is on a contour, remember. So you have to be careful. Okay, so you're substituting. Oh, by the way, so Jordan, I should ask, is there any other question on the topic we were talking about?
Nope.
Okay. Avinash?
No.
Yeah. So this is about the question number 4, I think, or 3?
3.
Question 3 deals with, there is an integral. I think it is this. Let me call it I.
It's 1 over.
There is an integral.
0 to 2 pi d phi by 1 minus e cos phi the whole square. I mean, there's some factors sitting in front, is r0, mu, and all
Minus,
that.
1
E
minus?
cos phi, eccentricity,
Whole
the whole square.
Yeah. Okay, great.
Yeah.
So first, let me address the contour one, because that is much more transparent in me, because I have taught this. So I kind of
That's why I approached. I
see,
thought I could make some sense.
Yeah, I could see the mistake you're making. So, but I suggested it, but then I didn't go through it very concretely. But so here is my point. So your point is that you're afraid that so we are making a substitution, that's z. This is not really a substitution. Notice, so you're saying, let me identify, or how do you say this? Yeah, cosine phi has this nice feature.
Yeah.
This is also z plus 1 over z over 2, correct?
Mm-hmm.
But notice, this is with the fact that magnitude of z is equal to 1. Only then.
Mm-hmm.
Agreed? It's not any complex number there. This is not a substitution to begin with.
Yeah, okay.
Okay. So this is equal to e raised to I phi plus e raised to minus I phi over 2. So this is not a substitution. This is, you're going into a complex plane. Right?
Yeah.
You're going into a complex plane. Magnitude of z is 1. So that means you're on a circle.
Mm-hmm.
Correct? And you're going from 0 to pi. That means you're starting from here, going all the way and coming back here. So that's a contour.
Mm-hmm.
It's not a substitution.
Okay.
Right? So you say that, okay, this integral is the same as integrating on a complex plane. Complex plane requires a contour. It turns out to be a closed contour. So that's your C. And d phi now, since you're on a unit circle, you say this is z is equal to e raised to phi. That's because magnitude of z is 1.
Mm-hmm.
Correct? So dz is equal to I times e raised to I phi d phi.
Mm-hmm.
So this is I, so this is
Iz.
dz over Iz, right?
Dz over Iz, yep.
Right. And then you have 1 over 1 minus e times e over 2 times z plus 1 over z.
Yeah. So now I don't really have to worry about the limits. It's just saying it's a closed integral and use the Cauchy-Riemann condition.
Exactly.
No,
exactly.
okay.
So because when you put in the limits, it became an open integral, and then it's a mess.
Yeah,
If
I was
it's an
figuring
open
something like a
integral, then you
minus
don't know.
1 to 1. I was doing a half a contour, I guess. Maybe something like that.
You were treating this as a substitution, I think.
Yeah.
Not a substitution. You're going from a real line to a complex plane. So it's a lot more happening there. Okay.
Okay. Yeah, that helps.
Okay. But To Avinash and Jordan, this is complex analysis. Probably you guys have not seen it because both of you have not taken math methods, right?
Mm-hmm.
So there are other ways to do this integral, but what I suggest is
I just solved using
uh-huh.
the integral 1 over a cosine phi.
Okay, yeah, that's good. Yeah, actually that's correct. And you take a derivative of that? Is that what you did?
Just I take 1 over a cosine phi to be 2 pi, which is 2 pi over square root of a squared minus 1.
Good, good.
And then I do the substitution where you end up with 2 over 2a times 2 pi square root of a squared minus 1. And then
I cannot see through what you're telling, but that's perfectly fine. Don't worry about it.
I get the correct
Don't
answer.
worry about this way of doing it. This is another way of doing it. Probably you will study in another course if you have not seen it. Kind of a neat trick, but yeah, don't worry about this. Okay. As far as you could do the integral, you're good. You're great.
Mm-hmm. I got the right answer, so hopefully it makes sense to me.
Okay. Good.
Okay. Yeah,
Nice.
that helps.
Okay. So this should solve your problem, correct, Angela?
Yeah, it does. It does. It does. Maybe I just need to refresh my memory. I needed to refresh it. That's all. Yeah.
Yeah. That's okay.
Okay. Thank you.
Okay. Good. Enjoy.
See you, everybody. Bye.
See you.
Yeah. Bye-bye, Jordan. Bye-bye,
Bye.
Avinash.
Have a
Just
good day.
for my information, sir, how many more homeworks do you have for this? Are you planning
For this, 2 more actually, but since you have done this ENM, that homework might be very similar. I haven't made it yet, so I
2 more
plan 2
homeworks
more.
for relativity, is it? In classical
Yeah, I
mechanics.
would like to, but there is not enough days. So maybe I'll make it 1 and the other optional.
Okay. And then
might
for
make it
ENM,
2.
how many more homeworks?
ENM surely 2, right? Did I not post? No, one. Yeah, it is. Yeah, today it will be posted. Yes. So there will be 2 more. Yeah, there will be 2 more. I think so. Yeah.
So you're saying retarded time and then 2 more in.
Yeah, from today onwards, 2 more. That's my plan. Yeah,
Okay.
again, I should make it optional so that you guys don't get pushed.
They're doing a similar thing. In
Did I tell that in the
ENM?
ENM class also, right? In the undergraduate ENM, I made 1 homework optional at the end, I guess.
Yes, that's what you said.
That seems reasonable. That way, see, my motivation is that, okay, as far as I'm concerned, I have given you a possibility for you guys to be exposed to something, and then if you guys have the time, you get to do it. Otherwise, it's okay. I'm not stressing you guys either.
Okay.
Yeah, so something like that I will do. Yeah, but keep asking me this so that I do it. Or there is a good chance that maybe there is only 1 homework. I don't know. It's work on me also. I have to actually design these problems and post it.
Yeah, it's a little bit overwhelming. I don't know, not the homeworks per se, but I don't know, the whole online thing, and then not the having the easy accessibility to ask you doubts. I remember coming to your office every now and then working it out with you. So it's, I mean, none of us signed up for online classes, right? This is like a.
How about this?
I mean, I'm not saying it sounds like a little bit entitled, even though we have all the resources and still we're complaining. But still, we didn't sign up for online courses. That's not something that, like, if we thought about it before and then just.
Yeah, I know.
It sounds like a personal problem.
You can extend this argument a lot. No, this argument can go very far because there is a lot to that. Yes, that's correct. But what I can suggest is the following. I'm usually almost every day, I'm available from 3 to 5. Okay. Feel free to call me on phone. I won't be there on Zoom. It seems very unproductive to me that I log into Zoom and sit there and no one comes. Okay. So what I suggest is that feel free to call me on phone. And I might say that, okay, I'll be there in 15 minutes or 20 minutes. If I'm doing something, I'll just stop that. And if you guys feel comfortable, do that. Is that good enough? Okay.
Yeah.
You need my number for that. Okay.
I think we all have your number. I have your number. I'm pretty sure.
I don't.
Okay, cool. Okay.
Avinash, do you have?
No, I do not.
Oh, you don't have. So this is my number, 405 401 2403. And be reasonable a little. Don't call me every day. Okay.
All I know about this situation is I'm getting dumber. Getting dumber and
You're
dumber.
getting what?
Dumber and dumber.
It's actually true. You feel like, I don't know, maybe because of lack of actual interaction or like with somebody. It's just, I don't know, we're in our own little hole and then, I don't know, trying to do the bare minimum for some reason. I don't know.
It's
doesn't
not,
feel like.
well, for me, it's not because of that. Whenever I'm inside of my room, I just feel heavy-headed and I feel dizzy. That's it.
Do you stay in a studio too? Are you staying in a small studio apartment like me as well? Yeah, honestly, right? It's just one room and then you move around.
No, I've been like that always. Like when I was in my home, my room is very big. Even then, if I stay inside of the room, I feel heavy-headed. I have to walk outside.
Mm-hmm. Yep. Yeah.
No. The best I can suggest is that, yes, even if it is for chatting, I can be available in the afternoons. Okay, even if it is just you guys want to, whine at things like this, that's also perfectly fine. I think I can take out that much time. Often it is productive, believe it or not, talking with you guys. Yeah. So in some sense, in the long run, I don't know, that's philosophical. Sometimes it's productive. Yeah. At least I believe in that. Yeah. So yeah, feel free, but don't call me and say, don't be quiet. At least talk. If you call me. Yeah, but feel free. I would say you're welcome to. Yeah. And I did suggest the students launch concept, but nothing has happened. But Bob was, I think you guys were in the chain of emails, right?
Mm-hmm.
So he surely will make it happen, but I think it has gone to the, what is it called? CTE, right? Technology people, and they are not very good at responding. So
Yeah,
maybe that will be
I think it's going to be a little late for the semester.
Yeah, by the time it gets done, it will be 2 weeks over and there'll be only exam week remaining. Yeah, I agree. But yeah, I don't know. What I can do is I can open this room. Sorry, go ahead.
Yeah, you think we're going to have this for the next semester as well, like fall semester?
Hey, we might. They've already found the third strain, so that means there's no vaccine. There's no vaccine in the foreseen future. So it might go away in summer, but it will come back in fall. We might have the same thing. And a few weeks before, they were thinking the virus is mutating slow enough to develop a vaccine. But now they found a third strain. They think, hey, this virus is actually mutating faster than we thought.
That's disappointing news.
And
I don't know. I don't know the answers. Yeah.
They are also proposing that in China, they had first strain circulating for like as many as 6 months before December. And they started reporting when they found the second strain, which is deadlier than first. And they're thinking the third is even deadlier than the second. Who knows? Who knows if we're going to get the fourth strain?
One way to look at it is that, yeah, I mean, all this could be true, but optimistically speaking, there is one data that comes up is that, assuming that is truth to that, is that China started in December and in March it reopened, right? So it took about 3 months for it to reopen. We ended in March 15th, we started, or March 1st in US cases began 1 week before March started.
But
So by end of May, I mean, again, optimistically speaking, this might go away. Let us stretch it to June, even then we are safe. So probably August is okay. But again, all this is based on a lot of ifs and buts. Don't trust me on this. People seem to be talking a lot of negativity out there. It's better to think optimistically.
So someone said this to me, and I read this somewhere, and I found it funny but true. You know, when you think about China, though, China is maybe not the best at reporting things because they still haven't reported the 1990 or 1989 Tiananmen Square protests to their people.
We're still recording just.
Yeah, they reported zero total deaths from Tiananmen Square.
Yeah, I read that too.
So maybe their reporting on the virus isn't so accurate either.
Yeah, no. That with that all that caveat, like I understand that, but again, for the optimism, you pick out all the good arguments, right?
Yeah, exactly.
Yeah, I mean,
That's what we
and then
want.
one thing that people are saying is there might be like a different like series of lockdowns sort of thing, because unless this is completely gone away, if you reopen again, there are chances of there being a spike again, right?
That's true.
Unless it's completely gone away and then we can have a vaccine or something completely eradicated. If you open again, there might be another spike. So might be like a series of lockdown or something like that.
You guys know as much as I know, as I know in these things.
Yeah, that's
But
true.
my simple thing is that this is what my sister tells me. My sister is a doctor, and she tells me that unless you get this virus in your body, so the virus is going to find bodies, like it needs bodies. Unless we develop immunity, this is not going anywhere.
I mean, it can happen. You can like catch the virus again, even if you recover, right? It's not like a chicken
That's
pox.
true,
No.
but chances are less.
No.
Hopefully, it doesn't mutate enough. So so the point is that if you catch it, and by the time you catch it second time, it mutates, then your immunity is useless, right?
Okay.
But assuming that it doesn't mutate, and what Avinash is talking about, first, second, and third, all that doesn't happen, then presumably we are better off. See, that's the uncertainty. So that's why people cannot play this game at the policy level, because there is so much uncertainties, and they have to defend. Like at an university level, my feeling is that they are playing it so safe because they are afraid of legals. Like people might complain that you opened and so many people died.
Mm-hmm.
University is liable to that. So there is a fear there, I think, in everyone. Even as a family, if you take it, if I'm a father of 3 kids, I might be ready to go out and say that, okay, I want to build immunity, I'm going to walk outside. But am I ready to do that for my kids, whom I feel responsible about? Probably not. So that's the dilemma that comes in. The university president might behave differently, but then when it comes to the legalities of how much responsible you are, they play a different game. Again, I'm not defending anyone. I'm not for anything here. I don't understand these things. So don't, like these are sensitive arguments, especially with the politics that goes in along with it. It gets extremely different game. Yeah. But yeah, I can see a little bit of problems in the decisions. Yeah.
Well, I heard Sweden is going on herd immunity route.
That's correct. Yeah.
So
honestly, I am sort of for that. But again,
yes,
herd immunity, what is that?
So herd immunity is something that, like, let's say a virus attacks a population, and if there is a herd immunity, let's say 60%, 65% of the people are immune to a disease, then a disease cannot it cannot grow into a pandemic. Just, you know, like the measles is these days because of herd immunity.
So they are actually exposing the people to virus.
Yes.
They're okay with people getting sick so that they develop herd immunity. Okay.
Yes.
Exactly.
So there is
So
no
they-
lockdown there. Is there no lockdown in Sweden?
No, there's no
It's only an
lockdown in
advisory.
Sweden.
Yeah.
They said
But there are lots of people dying also there.
they said Sweden has almost 12% of 12% of death rate in Sweden as of now.
But
So
it is
they're
not a
saying,
good comparison. See, that's why we shouldn't compare it now. That's an argument. Again, I'm not saying that I don't know what's going to happen, but there might be more deaths in Sweden now and maybe less later.
yes,
And
that's
if we
what
count all the deaths here, maybe it will be the same, but that's a maybe.
that's
It's an
exactly
uncertainty. So you cannot use it to convince anyone.
that's exactly what Sweden is saying. If this virus comes and fall, what are we gonna then? What are we gonna do then?
Yeah, that's the thing.
So if we have herd immunity now and just hope that it does not mutate.
Mm.
Or simplistically speaking, if you value life a lot, then you do whatever we are doing now. So you play it very safe as a policymaker. We are playing it very safe, which is what we should do. Every life is important.
Ethics is always a very confusing topic. I mean, moral ethics, like there is so many caveats to that. Like,
Yeah.
it's people who have learned about this their whole life, even they won't be able to find proper solutions to it unless a couple of physicists, sorry.
Yeah. And usually I try to think of it as whenever it's very easy to blame a policymaker. I always try to think, okay, ask your father. I mean, will your father do this to your kids? And they play differently. For themselves, they play it differently. When it comes to the kids, they play it differently because they have responsibility on them. And it's the same thing. Politics has both sides to it. So, yeah.
All right. So, thank you for the discussion, everybody. See you again later.
Yeah. Okay. Take care.
Bye.
Bye-bye.
Bye.
Okay. Bye, Jordan. Yeah. Bye, Avinash.
Bye.
Mm-hmm.